just to give Drummond a little bit more of an introduction, he received his PhD from UC Berkeley in 2018. I think he is famous for his beautiful visualizations, one of which is featured here, this plasmoid. I love it. I'm going to make a t-shirt with this on it. And his most recent paper in 2020 is the multiphase gas and the fractal nature of radiative turbulent mixing layers. And I really hope he shows some visualizations from that paper because it's an absolutely stunning piece of work. And so without further ado, I'm going to stop sharing and Drummond will take it away.
Thank you very much, Jess. All right, I think you guys are all seeing this. I'm gonna start sharing. I will say that's not my most recent paper. I wrote one since then, but which I won't talk about. I'll talk a lot about the turbulent mixing layer stuff. So first, I guess I'll just say I'm really excited to be here, and I was very excited to be asked to give this keynote, which at first I thought was a really great honor. And then I realized in many ways it was a curse because I'm the first theorist giving a keynote and there's just so much I wanted to cover. I didn't know what level to hit. So we'll see how this goes. But I'm really excited to talk about sort of the way I think about the multiphase CGM. Yeah, and so I guess I'll say one other thing. I've been a little distracted lately putting this together, as I think many of us have, and it's really exciting to be distracted by good news for once. And for me, not only did we have the inauguration yesterday, which was so exciting, but a few days ago I proposed to my girlfriend, and we are now engaged. So I'm very excited to be distracted by that as well. So I look forward to discussing that more over the coming weeks. It's really fun, although has taken my mind off the multiphase CGM a little bit. So I'll see what I can do. Thank you for all the emojis and clapping and everything. Okay, so here's the question, right? Why are gaseous halos often multiphase? Well, let's just get on the same page to begin with. Here's a little cartoon, okay? This is, I want to give a conceptual picture as a background, and then we'll build on this. So here's our nice little galaxy, and there's this, hot halo surrounding it. And this hot halo intentionally is not perfectly homogeneous, so there can be fluctuations and things within the hot halo itself. And we're here to talk about the multiphase CGM today, right? So let's add some multiphase. There could be many cold discrete clumps that sort of follow a biconical outflow and maybe some streams, or maybe the distinction between the phases isn't so clear and it's a little more blurry like this. Or maybe the multiphase is in the form of big streams that are penetrating the hot halo. Or maybe I was playing with my iPad too much and there's swirly outflows. But whatever, let's pick one, okay? So here will be our multiphase CGM, okay? There's, faint biconical outflow, maybe some streams, whatever. Don't read too much into it. So what do we have here? In the CGM in particular, well, there's the volume filling phase, okay? The volume filling hot phase that is roughly at the virial temperature, or maybe as Mark taught us in the first tutorial, this should be more like the gravitational temperature. And this is roughly 1,000,000 Kelvin or so. And this is, of course, a halo mass and redshift dependent statement, right? So lower mass halos are going to have lower virial temperatures, and therefore, the cooling will differ. Same higher halo masses will lead to much hotter halos. So something to keep in mind, but let's just keep this as a baseline number. Then, of course, as I've drawn, we have the dense phase. And this dense phase, I'm going to call it cold, although maybe to some people who study the ISM, this is abhorrent to call 10,000 Kelvin cold. But when I want to talk about lower temperatures, I'll call it maybe molecular or atomic. But and this cold temperature is set by roughly being in thermal equilibrium with the UV background, okay? And so that gives you a temperature of around 10,000 Kelvin. And of course, self-shielding can drive you to lower temperature, or can allow you to get to lower temperatures. Great. So those are the two phases, but of course this is a multi-phase CGM. So this is really, you know, there is a continuum of phases between here, or temperatures between here. And I want to highlight what I'll call the intermediate phase, which is sort of in between these two temperatures. And the reason why this is so crucial in particular is because at a temperature of around 100,000 Kelvin, this is where radiative cooling becomes incredibly important, and therefore where a lot of the most exciting and key physical processes take place. Okay, so I now want to outline what I view as the four primary sources of cold gas in the CGM. So first, and nearest and dearest to my heart, are galactic winds. So you can have a galactic wind directly launch cold and hot, of course, and hot gas out into the circumgalactic medium. Then you can also have satellite galaxies. And satellite galaxies, of course, they have their own galactic winds, and they can be stripped and therefore lead to cold CGM material. On top of that, you can consider accretion from the intergalactic medium. And then lastly, we'll talk about the thermal instabilities in the halo itself. And now for this fourth point, I'm not going to get into that much detail on this. We just heard a lot about this yesterday from Pratik Sharma. There's already been a really rich discussion on this, and Mark Voigt set up a little after party for this talk to talk about thermal instabilities even more. I will, of course, talk about this. I'll say off the bat that these are not distinct processes. They're all interconnected, but let me go through them one at a time, and then we'll talk about their interplay. Okay, so Todd Tripp showed the observer's favorite galactic wind system, what he called it, the exploding cigar galaxy, right? Well, I think this is now becoming the theorist's favorite example of a galactic wind. This is just this absolutely stunning volume rendering of one of Evan Schneider's recent seagulls simulations, showing the density volume rendering flowing out of one of these galaxies. And I'll talk more about this as I go. I think it's a really useful touchstone. And I want to ask two primary questions of galactic winds. First, how much cold gas is carried by the winds? Really like at the base, like how much is coming into the winds? And then what happens to the cold gas as the winds evolve? So let's start in the actual interstellar medium. I'm going to show some, Jess called me, I'm good at visualizations maybe, but the visualizations I'm going to show today are just out of this world by many other people. So here's a great one by Chang-Gu Kim. He actually custom tailored this one for me. And this is showing a small patch of the interstellar medium where they're actually resolving the star formation and supernova remnant processes within the interstellar medium, and then looking at the self-consistently generated multi-phase outflows that are flying out of this patch of the ISM. And you see all kinds of really rich dynamics. And one thing incredibly important for us is what you can see right here is you have a volume filling hot phase and a cold, 10 to the 4 Kelvin outflow co-moving or nearly co-moving with that hot phase. And so looking at this is really useful for sort of informing what we expect the phase structure to be at the base of the winds. And here I'm showing a way to look at this that I really like. This is from Chang-Gu's recent papers on this. And this shows the sound speed versus outflow velocity phase distribution. So the color shows how much the mass flux in this phase distribution, and hot stuff is up top and fast stuff is to the right. And so you can see there are two main sort of pockets. There's this hot, fast moving phase, right? That's this red stuff going really fast. And then there is this cool, 10,000 Kelvin stuff that's moving, maybe 30 kilometers per second or so. So if that's the baseline, that's telling us something very interesting, because if you're only going roughly 30 kilometers per second, then the cold phase is never going to make it out into the circumgalactic medium, and your most of the wind that the CGM sees will just be hot. And that may well be the case, and you would just have a sort of fountain flow of this stuff on, you know, the order of 5 to 10 kpc, depending on your halo potential and your gravitational potential from the galaxy. But there is also another possibility that this cold stuff becomes accelerated by this hot stuff, and they become roughly co-moving. And, you know, I may be striking a little bit too low of a level looking at the people who have their cameras on right now. I mean, everything I'm saying is really obvious. So just take this as sort of baseline framework for the discussion that we'll have afterwards. And I just want to briefly flash up some results from a student I've been working with, Raj Pandya. This is work that'll be published any day now, doing a very similar set of analyses on the fire simulation, showing the same phase distribution. And here we've shaded out the region that won't be able to make it out into the CGM. And so you can see all of this cold gas in this wind is really in the shaded region where it won't have enough specific energy to make it out into the halo. And this is measured, you know, right at the disk halo interface. So let's now think about this a little more, and I'll take some work from this great paper, I think a really seminal paper by Dong Zhang called Entrainment in Trouble. And it's the question of, how do you take a cold clump and accelerate it by a hot wind? So if this cold cloud has some density rho cloud and the size r cloud, then it's got a mass that's given by this, the density times the volume. And then you can ask, when does it become accelerated by this hot wind? And the answer is when it has interacted with as much mass in the hot phase as it has itself. And so you can sketch out this little cylinder, which, you know, the density is the hot phase density, the area is the cross-sectional area is the same as the cloud, and then the length is given by the velocity times this characteristic acceleration timescale. So we solve for T accel, or other people call it T drag, or whatever you want, and you get this very nice expression here, that the time scale on which the cold cloud is expected to become co-moving with the hot phase. Oops, I made the mistake of looking at the Slack. I'm going to ignore that for now. So you can look at this and say, okay, here's the acceleration timescale, and it's given by the ratio of the densities times the size of the cloud divided by the velocity. And I'll call this density ratio chi, the density contrast. So this seems good. However, as we've known for 30 plus years now, this is not all that happens. Here's a simulation by Matthew Abruzzo, another student I've been working with, showing this cloud crushing problem in action. And what you see is, very rapidly, the cloud is entirely destroyed. And Matthew is about the millionth person who has studied this, so I'm not going to even put the full list of simulations down here. But the point is that the destruction timescale is roughly the cloud crushing timescale, which is shorter by a factor of chi to the 1/2 than the acceleration timescale. So here is our first big conundrum. Okay, what does this say? Well, this says, right, that the destruction time is faster than the acceleration time, so then you don't get any entrainment. Any cold seeds in the wind will be shredded and mixed within just a few kiloparsecs, a few cloud crushing times. And so you don't expect galactic winds to be a predominant source of cold phase in the CGM. However, I have this great picture of Peng O and Max Gronke from 2018 when they were thinking about this. And what they realized at this moment of insight, this is like, I believe this is actually exactly when they thought about it. They realized that if the mixed gas cools more rapidly than the cloud is dispersed, then the cloud can survive. And this is an incredibly simple and very compelling idea that, to my mind, has revolutionized the way we think about multi-phase gas. And this, I mean, if you want to take one thing away, this is it. This is the important thing, okay? And really, you can just say it very simply mathematically. It's if the cooling time of the mixed phase, which is likely going to be the most rapidly cooling phase there is shorter than the destruction timescale, then your cloud will survive. And they flip this around to say, if your cloud is bigger than this characteristic cloud size, then it can survive. And so, I mean, this is fantastic. And let's see one of these in detail. This is again from Matthew Abruzzo, a paper that should be out any day now. And this is an otherwise identical simulation, but now cooling is turned on and it's more rapid than mixing. And what happens, instead of being dispersed, right, in the other simulation, the cloud was gone by now, it's actually growing. And you're building this long structure of, and the frame is following the cloud. So you're building this long cloud that's much more massive than what you started out with. And you can see there's a huge list of people. I think probably almost all of them are in attendance today who have been studying this. And to my mind, this is just beautiful, super exciting work. And I've been working on this problem myself and trying to really understand the mechanics of how this problem works by zooming in on just the turbulent radiative mixing layers, or TRML, or turmoil, or turmoil. I'm pushing this. This is Greg Bryan came up with one of the all-time great dad jokes, saying that this was taming the turmoil. I love it. So this is the way I like to think about it. So we've been zooming in on these turmoils and looking at it. So here I'll just show a brief visualization of this, showing the hot phase on top, the cold phase on the bottom. And what you have is that the shear flow leads to turbulence. That turbulence leads to mixing, right? Mixing of the two different phases. The mixing of the phases populates this intermediate temperature regime, which cools extremely rapidly. And that cooling then leads to an inflow, this blue color up here is an inflow from above into the cold phase. And so the cold phase is growing due to this cooling, which is induced by the mixing. Okay, so again, it's a very simple picture, exactly in line with the original picture by Max and Peng. And we were able to come up with a nice simple description of the growth rate of the cold phase, right? This inflow velocity is how fast the cold phase is growing. And it's parameterized just by, the densities, the size of your object, the turbulent velocities, and the cooling time with this sort of strange 1/4 power. And a few months after I came out with that, Brent Tan wrote a very exciting paper drawing on the turbulent combustion literature, right? So turbulent combustion is very similar to turbulent cooling, just with a minus sign. And so they had the great insight to look at this. And in particular, they looked at, this is another little, I don't know, the answer is in the mix, or Dom collar mix number, whatever. Okay, so they were able to extend this to the full range of cooling rates and show that the sort of power law behavior of the growth rate changes when this crucial number, which is roughly given by this, crosses above and below 1. So this is all really exciting. This has just been really 2 years since people have been thinking about this, and we've made really incredible strides, I think. And it's made a very compelling picture where you have this galactic wind and you put these little seeds, right? Like like we see in Chang'e simulations. And those seeds can then grow as they are accelerated and entrained by this hot wind, and can be a very important source of cold gas in the CGM. However, it's not quite so simple. So here is what I'd say. This is the figure. This one on the left, I've spent so much time looking at this figure, and I love it. And this is again from that same simulation by Evan, showing the temperature in a slice. And if you focus on this orange and blue, these orange and blue lines here, this shows the mass flux in this wind as a function of radius, where orange is the cold phase. I flipped the color. So orange is the purple stuff and blue is the orange stuff. That's maybe a little confusing, but bear with me. So what you see here is that beyond about 2 kiloparsecs, the cold phase is actually losing mass to the hot phase. Now, it's not entirely disappearing like you would expect for just, the no cooling case. And there is still cold gas flying out at, 8, 10 kiloparsecs from the galaxy. But this is a really important point that I think is something I'm actively working on. And I know Max is working on this, lots of people, and I think this is really exciting. And it's the dichotomy between the intrinsic turbulence in the mixing layer, right? The shear flow right on the skin of these clouds leads to some turbulence. But then you can also have turbulence in the background hot phase that can destroy the clouds. And so this simple picture is a little more complicated, although I think we're getting quite close to having all of the parts in place. Okay, so that's all I want to say for galactic winds. And I'm going to move on now to talk about satellite galaxies. Okay, so talk about a visualization. I mean, boy, this is from TNG 50. I assume Dylan made this. I just found this on their website. This is, boy, I love this. I could look at this forever. I could really just give my whole talk looking at this. This is a visualization of a protocluster forming, and you can see what I'm really interested in now are these little satellite galaxies with these beautiful clumpy streams behind them all over the place. The more you look, the more you see them. Okay, and so this is an example of how ram pressure stripping is really important for fueling the cold phase in the CGM. And in many ways, this is the exact same process as the cloud crushing process. Here's a simulation from Stephanie Tonneson that will be published shortly, showing a ram pressure stripped tail. And if those tails can cool faster than they're dispersed, then just like clouds in a wind, the tail can grow. And now this is actually complicated and maybe more exciting, because you also now have to think about self-gravity and potentially star formation in these tails. So a lot of the baseline physics is the same, although it is undoubtedly more complicated. So ram pressure stripping, though, is not the only source of cold gas from satellite galaxies. You can also look at just the winds from the satellites themselves. This is I think a really beautiful paper by Zach Haythan last year or 2 years ago, looking at the source of CGM material in the fire simulations. And what they show in brown here in these two different panels for two different times for the same halo is the satellite wind contribution to the CGM. And it's actually comparable to the actual wind contribution from the host galaxy. So this shows that satellite winds themselves can be extremely important for populating the CGM of a central galaxy. And on top of that, there's also this blue stuff, which is the direct IgM accretion, and they can all, as I advise you to look at Zach's paper for the details, but they can be, each of these can be very important contributions, each of these three channels. And so this leads me nicely to my next topic, which is exactly that, IgM accretion. So I'll again turn to Dylan Nelson for an incredible visualization. This is now 5-6 years old from the original Illustris, showing the density and temperature of a halo as you can see these cold, dense streams are penetrating this hot halo. And there's also, smooth accretion from beyond, and you get this, this really rich system. There's, of course, satellites and streams and everything. There's a very clear accretion shock as well. So there's all kinds of interesting dynamics, and it's worth thinking about the outside of the halo. So not just how gas gets out or how gas is added in situ, but also how gas comes in from beyond. And so I want to ask the question, or rather Neerman Delker asked the question in a really seminal series of papers with a great group of collaborators, ask what happens as these filaments enter into the hot halo. And here, imagine this is a filament, and this is a visualization of the density. So red and white is very high density, black is very low, and as this filament enters the halo, it mixes and is shredded into the background medium. And I'm sure many of you already know where I'm going with this. I'm sort of repeating myself. There's this process of shredding versus cooling, and if cooling wins, then things can be stabilized and the cold phase can grow. So here's an otherwise identical simulation that Neer did just recently with strong cooling, and you can see no longer is the filament shredded and disrupted. Instead, I mean, it still becomes very turbulent, but it remains very dense. And so this is an incredibly attractive way of getting cold gas into the CGM, you know, directly from the IGM on its way into the halo. And there's important observational differences that one could imagine from this. You know, this IGM accretion would be cold and dense, but it would likely be lower metallicity than, say, a galactic wind, which has been recently enriched. So I think there's a lot of observational characteristics that might be different from these different pathways that I would like to discuss further in the discussion. Okay, so I would be remiss if I didn't also talk about building the hot halo via IGM accretion, right? So as gas flows into the CGM, it can come in filaments, but it can also come in a smoother way and sort of interact with pre-existing material. And here's a set of simulations that I ran years and years ago now. It's actually this is a slide from a conference where I met many of you 4 years ago, my very first conference in Italy. I'm looking at Joe and Jess and Ben and a bunch of people who I hung out with there. I think that's where I met Jonathan, who's become one of my closest collaborators. So these simulations are, you know, fairly old at this point, and they are, I would say, a rehashing of very classic results dating back to the 70s and 80s, really crystallized by Yuval and Avishai in the early 2000s. You know, Dushan and Neil did great work on this. With, you know, this is a rich topic. So I'll just say, in short, as the gas comes in, accretion shocks against the existing material. If that accretion shock heated gas cools slowly, right, and slow relative to the free fall time, which is roughly the compression time, and so the heating time, and if it's longer than that, then the hot outer CGM grows. And there'll be all kinds of interesting dynamics. You can see clear signs of thermal instability and feedback in the center of this halo, which we'll talk about next. But it's important to realize that this is not always the case, right? This is where the virial temperature is 1,000,000 Kelvin. But what if the virial temperature is 100,000 Kelvin, right? And this is a 10 times lower halo mass where the accretion shock heated gas cools very rapidly. Then you have an incredibly different CGM where it's, you know, feedback and turbulence really rule the day, and you have something that looks very different, and the whole system will be out of pressure equilibrium. There'll be sort of global thermal instabilities as opposed to local thermal instabilities. And well, let's actually get into that right now. Okay, so let's get into thermal instabilities. So let me check my time. All right, I got 17 minutes by my clock. This is going to be a little tighter than I thought. I'm like not halfway through, so it'll be a little tighter, but I promise I won't go over. Okay, so thermal instabilities, right? Mark promised everyone that I would talk about this, so I better talk about this. I want to make a distinction, which is actually maybe less of a distinction than it should be, that it's important to consider what the background is that you're talking about that is thermally unstable, okay? So you can have a background that is in what's called a cooling flow. And a cooling flow, to my mind, should be thought of as the basic property of the CGM. You know, it's accretion shock heated from out beyond, and then it's really just sitting there. And what is it going to do? It's going to gradually cool and flow in. And that's a cooling flow, okay? And it's where your losses dominate your heating terms. On the other extreme, you can have a halo where there is complete thermal balance, where the cooling losses are balanced by your heating, right? So this is where, you know, feedback is able to do a perfect job and balance your cooling losses. And now I want to be, there's been a lot of discussion about this stuff, so I want to be really clear to say, I'm showing here the two extremes. I do not think the universe lives at one of the extremes. There is the continuum, you know. It might be that the losses are close to the heating, but not exactly balanced, and so you've got some bit of a cooling flow and some bit of a, a thermal balance. And so I think it's important to keep that distinction in mind when I talk about this, and that this is really a continuum. So let me just explain a cooling flow for those who don't think about it all the time. It's quite a simple idea, which is just that the compression of gas balances its cooling. So you have a parcel of gas, it's out in the CGM, it cools, it loses some entropy, and it falls in. And as it does, it's compressed and it's heated. So what ends up happening is it stays at almost exactly the same temperature as it flows in and as the entropy is decreasing. I recommend people look at Jonathan's recent series of papers on this if you're interested in some very intuitive, nice, like 3 lines to understand these. And there's one crucial property of a cooling flow, which is that the cooling time is equal to the flow time. Okay, and by flow time, I just mean, R over V. So your cooling time is balanced by the flow time. And if you up the cooling, you up the inflow. And you can keep doing that. There's different ways you can up the cooling. You can increase the density. You can, decrease the overall temperature because you're in a lower mass halo, right? Whatever you do, if you increase the cooling, you're going to up the inflows. And that's fine. Nothing changes until, right? Well, eventually, as you do this, right, your sound speed stays the same. But if your velocity is going up, then something's got to give, because eventually you'll become supersonic. And there's a bunch of really classic results on this dating back to Balbus and Soker in '89 and probably people before then, which showed that cooling flows become thermally unstable when they are supersonic. And this supersonic transition, because of this, occurs when your cooling time is less than your free fall time. So, this is, I think, a very common situation. And really what you can think of, it's just, once you're supersonic, you're out of sonic contact with your neighbors, so perturbations can sort of run away and cool faster than it's communicated to their neighbors. So this is the picture of a supersonic cooling flow, or really the transition from subsonic to transonic to supersonic. And this is something Jonathan and I have been looking at in a bunch of different guises. Here's a recent paper that he and Claude André led looking at the fire simulations. This is a visualization of the temperature field in the inner CGM at fairly closely separated in time. And the main difference in these halos, what happens over this time, is it transitions from a supersonic on the left to a subsonic cooling flow on the right. So there's going to be lots of discussion about this in the after party, Mark's after party on thermal instability. So I suggest we, talk more about this there. But you can clearly see that this is a thermally stable medium that's almost uniform temperature, and this is a thermally unstable medium that has, huge temperature variations. Okay, so now there is this whole other branch of thermal instability, which is actually, I think, really the hot topic. And this is what we heard so much about from Pratik Sharma yesterday. And so I'm not going to get into too much detail on this now because we did just discuss it, but I want to show the basic principle and also just reiterate that these two processes, these two ways of looking at it are not incompatible with each other. They might be happening at different times in different places, or some continuum of the two. And so here is the other end of the spectrum where you have thermal balance. And these are visualizations done by Irina Butsky in a paper that we put out last year, looking at how thermal instability changes in the presence of cosmic rays. This is actually, since I'm not touching on non-thermal pressure at all this week, I'm showing the hydrodynamic only simulations. And what we've got here is a hydrostatic stratified medium where at every height you balance heating with cooling and you put in little perturbations. And the one on the left has very rapid cooling and the one on the right has very slow cooling. And they're going to evolve very differently. So the one on the left cools so rapidly that it doesn't even fall down prior to, cooling out. And the ones on the right, they don't even cool at all. And there's one very important point I should make about these simulations is these are run for the same number of cooling times. So these simulations have very different free fall times. So this simulation was run for 100 times longer than this simulation. That's why, this stuff hasn't even fallen down. So the one on the left really has way, way more cold gas. And this is exactly the process that Pratik was talking about yesterday that Mike McCourt showed in his seminal 2012 paper, followed up by Pratik's seminal spherical paper, in spherical coordinates. There's so much work on this. I'm going to miss references, so I'm almost scared to do this. But Yuan Li did great work on this with Greg Bryant. Suching Ji looked at it in MHD. Irina and I did this in cosmic rays, building on some really, really beautiful work, theoretical work by Philip Kempsky. So there's lots going on here, and I think we should discuss this more coming up. And that's sort of all I want to do now for my overview. Of course, my overview has taken most of my time, and I want to stress before I move on that these are not happening in isolation. Cosmological accretion, satellite galaxies, they trigger thermal instabilities, right? Large mode density perturbations like Pakriti Palchowdhury showed trigger thermal instabilities more easily, just like what I think Clark Asmarian and Dylan Nelson are seeing in their cosmological simulations. And those thermal instabilities then feed cold gas into the galaxy, which then drive galactic winds. So this is a rich, interconnected system, right? And so there's a lot going on here, and there's probably different observational characteristics of all of them that we should think about. And so now that I've done that overview, I want to sort of get a little more meta, right? And think about, what is this question? Why are gaseous halos often multi-phase? And I'll give you my answer, which is, it's sort of like you spin the wheel of fortune, and whatever you land on, you can get multi-phase gas, okay? So you spin the wheel of fortune. Whoops, what did I do? And you can get multi-phase gas because the cooling time is less than the cloud crushing time, like Max and Peng showed. Or you can get multi-phase gas because the cooling time is less than the ram pressure stripping time, like Stephanie Tonneson showed. Or the Kelvin-Helmholtz time, like, a bunch of us have been showing, like Nir showed and Brent showed, and I've been looking at. You can also get it if the cooling time is faster than the compression time, like, Yuval and Avishai showed us in 2003, or even, back 50 years from now, or whatever, 50 years back when they first started thinking about this. Cool. Okay, so you can also get it if the cooling time is less than the free fall time, or maybe 10 times the free fall time. And to just sort of synthesize it, the way I like to think about it is just the mixing time. All of these things are, in a sense, the time scale on which you're mixed back away from multi-phase. If you take something that's inhomogeneous, these are sort of the timescales on which you become homogeneous. Your cloud crushing, it's mixed back in. Your free fall time, it's buoyancy waves, and whatever it is, it's effectively a mixing time. So this is maybe a little too imprecise to really be useful, and so I'm not trying to say this like quantitatively, because I do think the details really matter. But on a 0th order level, this is my answer, right? Because your cooling time can be less, and is oftentimes less than whatever the relevant mixing time you're looking at. So I've got 6 minutes left by my clock, and there's a few questions I want to address, okay? So this is almost a command performance because, oh, Jess is giving me 10 minutes left? Okay, great. Well, then I'll slow down. So cool. So are the phases in pressure equilibrium? This is a question that's been coming up a lot in the observations that Mark told everyone I was going to talk about, so I had better talk about it. So let's get into it a little bit. And again, this might be a little too simplistic to be super useful, but I think it's the way I think about it, and I'm the keynote speaker, so you're going to hear about it. So the answer is yes, unless, okay? And that unless is, there's really 3 things, although actually there's 4, but so unless they're moving too fast. So you should be in pressure equilibrium unless your flow time is shorter than your sound crossing time. I'll get into each of these afterwards, so you don't have to dig in too much now. Also, they can be out of pressure equilibrium if they're cooling too fast. So if your cooling time is less than your sound crossing time, or if you don't have enough resolution. So if your cooling time is less than sort of the sound crossing time of one of your cells in a numerical simulation. And then, of course, you know, I'm just completely punching on this. I have tons to say on this, but non-thermal pressure is awesome. Irina Butsky's paper on this is a really nice look at this, I think, in a controlled way with some nice models. But everyone here really, I think, is chomping at the bit to discuss this. So here's the, you know, setting up the discussion for next week. So let's talk, though, about these 3 and how these take you out of pressure equilibrium. So first, let's consider supersonic motion. Imagine you have some background hot phase that you're considering. Maybe this is a wedge of the CGM or some outflowing galactic wind, and it has some pressure scale height h over which the pressure changes appreciably. Well, in this case, imagine you have a filament like Near Mendelker considered. You could also consider a cold cloud flying out in the other direction. And this filament is coming in at some velocity v, and it's got some, you know, sound speed and some size r. Then you are likely to be out of pressure equilibrium if you traverse the scale height faster than pressure can communicate across the thickness of the filament, right? So this is, you know, this is not I think a contentious statement, right? It's if your flow time is shorter than your cooling, or than the sound crossing time, then you are likely to be out of pressure equilibrium. But this is not going to happen for a really long time. You know, this is not likely to be long-lived. And I think this is a point I want to stress. Supersonic motion doesn't go on for a long time. Sort of by the very nature of being supersonic, it wants to make shocks and slow things down. So you're likely to slow down and not be out of pressure equilibrium for too long. You can also consider supersonic cooling. This is something that Mike McCourt looked at in his seminal shattering paper a few years ago, and also Max and Peng looked at really nicely just last year in a very intriguing, I would say, letter that I want to dig into and understand even more. And what they did is they start with a potato, as Max calls it, an inhomogeneous cloud, and they let it cool. And depending on the size of the cloud, it cools in an isobaric way, or it cools in an isochoric way, you know, out of pressure equilibrium or in pressure equilibrium. And just focusing on the one that cools out of pressure equilibrium, here, that's this guy. Here's a visualization of the pressure of the simulation. Originally, it's in perfect pressure balance, and then they let it cool, and it goes out of pressure equilibrium, although it then quickly comes back into pressure equilibrium. Oops. And characteristic size scale, I mean, the characteristic criterion is if, you know, the cooling time is shorter than the sound crossing time, or if, you know, another way to say that, if the cloud radius is bigger than CST cool, you know, if the cloud is larger, then a sound wave can communicate across the cloud, which they call L shatter, because it does cool things to your cloud. So I'll say to my mind, the poster child for being out of pressure equilibrium, because I think it's actually one that can be long-lived, is a supersonic cooling flow. And the reason why this is the poster child is because it's both cooling too fast and moving too fast. Okay, and this is actually, I think, a very common situation in the universe at high redshift where the densities are high. You're likely to get these supersonic cooling flows, and you know, turbulence and feedback is only going to make this even more out of pressure equilibrium. And so the reason why you're out of both, you know, you're both moving too fast and cooling too fast is because of you have both of these criterions. And Jonathan visualized this really nicely in his paper. These are those same slices I showed you earlier, but now showing the pressure deviation. And what you can see is in the subsonic cooling flow over here on the right, the pressure deviates, you know, order unity, really. But when you go down here, the pressure deviates by, you know, a factor of 100 over relatively small scales. And so this may be the state of the universe for large swaths of cosmic time. And in particular, you know, high redshift observations, we need to consider that this is the sort of medium that we're looking at, as opposed to, you know, this with some cold droplets in it. So this is a point I think is worth stressing. I forget what's next. Oh yeah, okay. So being out of pressure equilibrium because you're under resolved. I talked about this at the last KITP meeting, so I won't get into too much detail, but I think it's worth noting because so many of us run simulations of the CGM. If you take one of my turmoil simulations, like I'm showing over here on the right, the turbulent radiative mixing layer, and you ask, what's the phase distribution? Right, then here's one way of visualizing it. So this is the mass, how it's distributed in pressure, high pressure to the right, low pressure to the left, versus entropy, high entropy up top, low entropy on the bottom. And you see a very nice trend. It's pressure equilibrium, and then a dip to low pressure, right? And so this is out of pressure equilibrium. However, if we increase the resolution by a factor of 4, that dip diminishes. If we increase by even more, that dip vanishes. Okay, so if you want to talk about, you know, the phase structure of your simulations, you better be resolving things properly. And of course, these are pure hydro simulations. You know, non-thermal pressure can really add to this picture and maybe change the resolution requirements. But it's worth keeping this picture as sort of the baseline and then adding to it, I think. And we can understand this very simply. In the color that I've overplotted, this is at every point you can ask what's the sound speed and the cooling time. And so here I'm now plotting how the sound speed times the cooling time changes over this domain. And I've drawn a little fuchsia line here to highlight the resolution of this simulation. And what you can see is in the low resolution simulation, it remains isobaric at constant pressure until it approaches the resolution limit where it dips down. At intermediate resolutions, it dips right alongside resolution limit, where at very, very high resolution, you know, the resolution limit is way over here, so we're totally safe. Great. So this is something we want to keep in mind because these turmoil simulations, even this low resolution one, is impossibly high resolution for a global simulation. Maybe not impossible, because there's been some really great work in recent years, or really in the recent year or two, trying to enhance the resolution out in the halo. And I'm pretty confident they're not getting down to this sort of resolution. But there are different questions one might want to ask. If we're asking pressure equilibrium, you do need to resolve CST. I'm confident on that. If you're simply asking how much cold gas is there, well, that's actually a slightly different question, and you might get away with resolving just the turbulent mixing, which is a little less restrictive of a requirement, although I'd be keen to talk more about this with everyone. in the discussion and over the coming months, or coming, yeah, I guess months. So in my final, say, 3 minutes, I just want to give, my perspective on what the observational tracers of the multiphase CGM are actually probing. So first, let's make a multiphase CGM, and we'll do it in my favorite way, which is to make the cooling time shorter than the mixing time. So this is very simple. Take a turbulent box, stir it up, make the cooling time shorter than the mixing time, and you get this very nice looking swirling bath that's clearly got, 2 stable equilibria, the hot phase and the cold phase, and lots of intermediate temperature gas. So I could stare at this all day. I won't. And instead, I'll overplot what this looks like in different ions. So here is the number density of oxygen 6, carbon 4, neutral hydrogen, and silicon 2. Okay, and I'll fix time, but I'll swipe these through so you can see how the different structures look. And I want you to imagine you're putting, a quasar sightline through this. Well, let's focus up here, okay? So what you see here is, first, let's go to, here's silicon 2, okay? These cold clumps are traced really nicely by silicon 2. There's a whole bunch of them. You'd have a whole bunch of cool lines probably blended together if you didn't have high enough spectral resolution. They'd also be traced in H1. It'd be surrounded by a cocoon of strong carbon 4 and a little bit of O6, so not sort of a booming O6 signal. If instead we look over here, you can see there's no silicon 2, just a little bit neutral hydrogen, okay, some carbon 4, and a ton of O6. So I don't know if this is really useful, but I just kind of wanted to put this up as an example of what I imagine in my head when I see your spectra and I see the bumps and wiggles. And I think we're getting pretty close to being able to really understand the physics of multiphase gas. And so pretty soon, I think or maybe even we're there now. It's time to start forward modeling these observations and really trying to understand them. Okay, so I'm gonna stop here, and here's my beautiful cartoon summarizing everything, that the CGM is a rich interplay of these things we've talked about. Yeah, and I'll stop there. Thank you.
Yeah, let's everybody give Drummond a round of applause. That was a ton of incredible, beautiful visualizations, as expected, did not disappoint, including a lot of really, really interesting material for discussion. So the Halo 21 Week 2 Multiphase Slack channel is already blowing up. If you haven't been over there, read it over. Add your own comments and questions. We've already got, I've written down a few things that we want to talk about with our panel when we come back. Take 5 minutes to do that. Let's come back at 9:06 a.m. Pacific time in 5 minutes, where we'll resume with our panel discussion and questions, and make sure you head over to the Slack. Thanks, everybody. Thanks again, Drummond.